A projectile is fired with an initial speed of 200 meters per second and angle of elevation is 60 degrees. Okay, that is 60 degrees. Find the range of the projectile, so how far it reaches on ground, the maximum height reached. So this is in, we can say, in x direction, and this one in y direction, so how high it reaches, and the speed at impact. So when it hits the ground, what is the speed? So by the way, speed is magnitude of the velocity. So in this case, initial velocity all the time v, when time is 0, just the initial speed cosine of angle, that's 60. So 200 cosine 60 comma 200 sine 60. Cosine 60 is 1/2, so 100. Sine 60 is √3/2, so 100 √3. For these problems, we always start with the acceleration, because we know that part. Acceleration vector is in fact some meters, right? So we are neglecting the air resistance, but we have acceleration due to gravity, that's 9.8. And it's acting downward, so there is no horizontal component, just the vertical component and downward, so negative and j, vector j component, not I, 0 component. This is same as if we write in terms of components, so 0, negative, comma negative 9.8. That's the acceleration. Now we integrate both sides, okay, and we get velocity. On integration, we get velocity equals just 0, because there was nothing, and that's negative 9.8 t plus c1, this constant of integration, c1 vector. Now we use the initial velocity to find c1. So using v0, which is 100 comma 100 √3, we are basically taking t equals 0. So this v0 is 100 √3 equals 0. Plug in t equals 0, so this becomes 0 as well, 0 0 plus c1. So this 0 0 is nothing, so c1 vector is in fact just this 100 √3. Okay, now we substitute this back here, then we get velocity. Then velocity vector is equal to this vector plus 100 √3. So 0 plus 100, just 100, and this vector plus 100 √3, negative 9.8 t plus 100 √3. Now if we integrate this velocity, we get position. So on integration with respect to time t, so we get position at any time t is equal to antiderivative of 100 t, okay, two terms, so antiderivative t square over 2, so negative 4.9 t square plus 100 √3 t plus constant of integration. Now to find c2, we're going to use initial position, and look at here, we can say this is at the beginning 0 0 position, okay, just the initial position. Yes, 0 is 0 0, that means c2 will be just 0 0. Okay, initial position is 0 0, so c2 is also 0 0, so we don't have to worry about anything. We don't have to find c2. Even if you find c2 vector, that will be 0 0. Okay, thus the initial vector, sorry, the position at any time t is 100 t comma negative 4.9 t square plus 100 √3 t. Now we have this velocity vector here, and we have position at any time t vector. Using this we can answer anything, by the way. The range of the projectile, okay, so that means, look at this, we want this distance, which is in fact x component, okay, and we know that when it hits the ground again, the height part, the height or the elevation will be 0. So this is the position function. The first part is x direction, and this is the height part, okay, this is x direction, this is y, so up down, this is right left, and this one, since it hits the ground, so this height part will be 0. Okay, to find the time needed by the projectile to hit the ground, we said this equals 0. So we said this negative 4.9 t square plus 100 root 3 t equals 0 to find the time when it hits the ground. Now solve this equation for t to find the time. So we got two terms, we can factor t out. That leaves negative 4.9 t plus 100 root 3 equals 0. So either t equals 0, and that's at the initial, so we don't take that. So this equals 0. Second part, 4 minus 4.9 t plus 100 root 3 equals 0. Move this over, divide by negative 4.9, we get t value. Okay, that means t equals, we get t is about 35.35 seconds. Now to find this horizontal direction, that means x, we look at this position function here and plug in t equals 35.35 here. Thus in part A, the range A is equal to 100t, so 100 times 35.35, so that's approximate value, so this is 35 meters. Okay, in part B, we are asked to find how high. Let me read the question. In part B, the maximum height reached, look at here, this is the maximum height. At maximum height, the velocity will be 0, so we can find the time. But look at here, to get to this point, it took about 35.35 seconds. So to get to the highest point, then it will be half of that time. We just take the half of this time, and to find height at that point, so basically we take the y component of the position. So here is the position function, every single time here is the position function, and we plug in that t. Okay, for the max height, the time will be half of this, so let me write that here. So this is the time, half of this time is the time to get to the max height, and the max height is given by this is the position function here, and this is horizontal, this is vertical, so we plug in t equals 17.68 here, then we get that about, let me calculate, it will be about 1530 meters. Now in part C, we need to find the speed at impact. So when it hits the ground here, we need to find the speed. So speed is magnitude of velocity, so we need to find the velocity at the impact. Okay, and where is the velocity function? So here is the velocity function, and we know the time required to get there, to hit the ground. The time is 35.35, so we plug this time here, then we get the velocity at impact, and when we take the magnitude, that will be the speed. That will be the speed we are looking for. Okay, so let me calculate here. So the velocity at impact, so go up here, just plug in t equals 35.35, so we get velocity. Then speed is just the magnitude of this velocity. That comes out to be 200 meters per second. Final